You guys are aware of all of the algebra that we have done so far, from Algebra 1, maybe even from 7th and 8th grade math up until 3 days ago, has always been with the Cartesian plane kind of in the background, right? Okay, the Cartesian plane being kind of the tie-in to all of our algebra and all of our geometry. We've been dealing with this thing over here on the left, the green graph, which we call it. You guys may your coordinate plane. It's defined as the Cartesian plane. It's named after the founder, Rene Descartes, or the inventor of it. But it's what we refer to as rectangular coordinates. Okay, meaning that if I want to move from C to A, no matter where C and A are. Okay, I just chose the origin and then just some random point 2, 3.46. I can move from C to A by moving in directions that are perpendicular to one another, right? Okay, and that's one option. There's actually an infinite number of different routes I can take to go from C to A, right? I could maybe one other route would be from you go up to, over to, and then up that 1.46 that would remain, right? But every one of those blue movements was perpendicular to another blue movement, right? And however you move in the Cartesian plane, or the XY coordinate system, that's what you do. You move in perpendicular movements, okay? So we refer to that as a rectangular coordinate system. Okay, rectangular meaning that things are perpendicular, right? Does that make sense? Okay. Well, sometimes it might be a little bit easier to say, nope, I don't want to move rectangular. I want to move straight from C to A. Because shouldn't that be a shorter distance? All right, so what we do, instead of moving rectangularly, we kind of implant circles on top of our graph, and we move at particular angles. Okay, so this point right here, okay, let me get a standard view here. Okay, let's go to standard view here. Would you agree that those things kind of look to scale? A to C in the green and A to C in the yellow. They look the same, don't they? Because they are. C is the exact same point in both graphs. A is the exact same point in both graphs. Okay? And remember, what we do with graphs is it's being able to locate a position in some space, whether it's two-dimensional space or three-dimensional space. Here, just talking about two-dimensional space, I can get from C to A by moving left and right, up and down. Or in the yellow one, which is our polar system, we can move from C to A by discussing on which circle do we move out from C onto. Okay? So do you guys agree that A would be on the 1, 2, 3, 4th circle from C? Okay, everybody see that? Okay. And then at what angle from the positive x-axis? And we're going to rename it a little bit later. But basically saying, okay, if I'm on the 4th circle, what is this angle that I would have to travel to get to A? And that angle would be what? Pi over 3. Okay? So basically the same, give yourself kind of a bird's eye view. Let's say you're at C and you want to get to A. Okay? You say, okay, I'm going to position myself, so I'm going to move at a 60-degree angle. And I now know I'm going to walk at a radius of 4 or a length of 4. And I start walking in that direction, and I walk that total distance, and I stop. I'm at the exact same point that somebody would have moved in the green coordinate system 2 units to the right and 3.46 units up. Does that make sense? Okay. But you did it in a much more efficient way in the yellow because you're moving along the hypotenuse of a right triangle. Would you guys agree with that? Would you say that this, let's see here, this movement here to there, and I merge those two things together, would the A to C in the yellow be the hypotenuse of the triangle in the green? Does that make sense? Okay. So we know that A squared plus B squared has got to be equal to C squared. So C squared is or I guess C is a shorter distance than the culmination of C to B and then B to A. Is that all right, everybody? Okay. So let's kind of talk about how we label things and define things in this system. So hopefully, kind of that demonstration there is showing you that if I want to get to a point in space, a point in two-dimensional space, I have multiple ways of doing that. And you can create any system that you want to. You guys have all looked at an atlas before, right? Okay, like a road map. Okay. If I'm looking at a road map, let me just see here. If you guys were, let's say that we're looking at so we're looking at Ohio, and we've got A, B, C, D, and then 1, 2, 3, 4. Okay. If I said I wanted to find Columbus, okay, and I look in the index, it's going to say B2, isn't it? You guys ever done that before? Okay. So then I look in the column of B, and I look in the row of 2. Okay, and then wherever, they don't go B.5 or 2.5 or anything like that. So they give me the closest intersection of grid lines, and then I got to look at the map and say, okay, now where's Columbus in comparison to that, right? But it's a defined, it's a structured manner of how to find and identify locations in space. Does that make sense? And you can do anything, any kind of construction you want to make, so that you can follow it and get to from one spot to another spot consistently. You can create a coordinate system. Okay, there's many coordinate systems out there. We're just now trying to focus on the polar coordinate system. Okay, so rehash. It says in rectangular coordinates, we break up the plane into a grid of horizontal and vertical lines. We'll locate a point by defining the intersection of a vertical and horizontal line. Okay. In the polar coordinates, we break the plane up into circles. It's the exact same plane, but we break it up into circles and then rays emanating from those circles. And usually we use those rays to be increments of 15, 30, those types of degrees. Okay. Going 1 degree is kind of crazy. We have 360 rays coming out of that thing. That'd be messy. But a point is defined as the intersection of a circle and one of those emanating rays. Okay, so kind of do a couple examples here, and I have to animate this to view it the way I want to see it. So let's see here. All right. So in a rectangular system, the origin is 0, 0, right? Okay. Well, the 0th circle at 0 degrees or 0 radians, okay, is referred to as the pole. Okay. So the origin and the pole are analogous to one another. Does that make sense? They match up. Okay. The polar axis is from the pole, and then you move along what would be the positive x-axis in rectangular coordinates. Okay? So that's called our polar axis. And if you think about anything that we've done up until now with trigonometry, that has always been your initial ray, hasn't it? No matter what angle you've traced out, your polar axis is your initial ray. And that's, for the most part, the way we're going to think about it. Okay? It's our initial ray for moving somewhere around these circles. Okay? Every point, okay, are represented by a radius and an angle. So every ordered pair is going to be an r, comma, some theta. R being the radius, and theta being the angle of rotation. When we say radius, it just tells us the circle that our point is on. Okay, so I'm going to kind of hop out of this real quick and show you what I was doing over here. So this point A, so you see when I highlight A, it knows that A is the same point in both systems. Okay. Right now, A is located as an x comma y. So over 2 and up 3.46. And that's really what's going on over here as well. Okay. But when I change it to polar coordinates, you see now how it says go off the fourth circle, 1, 2, 3, fourth circle at an angle of 60 degrees. Does that kind of make sense? Okay. So that's where we're seeing the r comma theta. Now, GeoGebra has a little bit of a difference, because if I type in 4 comma 60 degrees, it doesn't know what to do. So it uses a semicolon. Don't worry about that. We're still use commas when we write stuff by hand. But when it asked me to plot some point, okay, so the point that I want to plot is 5 comma pi over 4. Okay, and you can do this either way. You can either find the fifth circle first, okay, and then go out pi over 4 radians on that circle, or you go out find the pi over 4 radians first and then count out to the fifth circle. I think in this one, I've got to say find the angle first. So obviously, my answer then has to be on that pi over 4 ray. Does that make sense? Okay, and my point has to show up on there. And then we count out 1, 2, 3, 4, 5 circles. And the intersection then of that fifth circle and that pi over 4 ray, that point right there is 5 comma pi over 4. Okay. If we were to put a grid over the top of it, we should be able to find the rectangular coordinates for that point as well. Okay, so every time you have rectangular coordinates, it's 0.2 comma 3, for instance, we should be able to figure out what it is in regards to polar coordinates. Okay, and our SOHCAHTOA and Pythagorean theorem are actually going to be the things that allow us to get there. Okay, and it's actually pretty easy to think about. What is interesting is if I asked you to name a point okay, if I'm in this green graph, okay, and I want to name the point 2, 4, so I plot 2 comma 4, okay, is there any other name that I can give that? Any other set of coordinates, I guess, that I can give that are different than 2, 4, but provide the same exact point? If I type in 2, 4, again, it's going to be the same point on top, right? If I type in another set of numbers, is it going to get me to that point? No, it's going to give me somewhere else, right? And what that means is in the rectangular coordinate system, the coordinates are unique, meaning that your point can only have one x value and one y value, and they can ever differentiate or ever differ, I guess. Because once they do, they get you to a different spot, don't they? Let me see if I can maybe kind of prove this to you over here. Let's say that I type in 4. All right, I think I can do this. Let's see here. All right, so 4 comma 60 degrees gave me that point D, right? Is there an angle that is coterminal with 60 that you guys know about? Is 420 coterminal? Would it mean the same spot? Okay. Now you did see that I had 4, comma 420 in there. Okay. It's going to always, GeoGebra has the work to always reduce it to the smallest positive angle. Okay. But if I type in 4, negative 300. Give me the same point. Okay. So we've got 3 points here that are all looking at the same position in space, but all defined differently. One is 460, one is 420, one is 4 negative 300. So that's the thing that's kind of different about ordered pairs in the polar system, is that they're not unique, meaning that any point actually has an infinite number of ways you can define it in regards to its ordered pairs r, comma, theta. Does that make sense? Okay. And it all has to do with coterminal angles. Okay. I can keep doing that as long as I need to, as long as I want to keep getting the same point. And I can also do what would this angle right here be if each one of these is 30? So that's 30, 60, 90, 120, 150, 180, 210, 240, right? Let me do this. Let's say that I type in negative 4, 240. Let's see what happens there. It gets me back to the same spot, G. Okay? Even though I typed in a negative radius in a 240 degrees. Okay? So there's a lot of different ways, and I can add 360 to that number. Negative 4 plus 600 would be another way of labeling that point. Okay? That can be a really, really, really nice thing, and it can also kind of be a headache in regards to, I asked you guys to name a point. In rectangular system, that's easy to grade, right? Everybody should have the same exact thing. But in polar, we've got 25 different answers, and every one of them be right. Does that make sense? Okay. But it does allow for us to do some nice things. You see up there on the board, I have 2 plus 3i. I had it to the second power. Okay. And you guys know how to do that. You know how to FOIL that, right? Okay. Really nice, easy thing to do. Okay. But when that power goes to 5, 6, 7, 8, I don't want to have to FOIL something out 8 times, right? Okay. I think I had 12 up there. I don't want to do that. What happens is that polar coordinates allow us to be able to eventually graph complex coordinates, complex numbers. We haven't done that yet, right? We don't know how to graph complex numbers. Polar coordinates will allow us to do this, okay? And then in polar form, it allows us to take something like 2 plus 3i to the 12th or 2 plus 3i to the 120th power and actually do that foiling process extremely fast. Okay. And then if we need to, we can convert back to rectangular to get the answer in rectangular form. But it is very, very convenient for kind of higher level calculations. Okay. So that's kind of where we'll take this stuff, is to see how it can benefit us, maybe through the use of technology and that kind of stuff.